Welcome to Chapter 2, Earth in Space, from The Good Earth, an Introduction to Earth Science. Again, I am your instructor, Dave Cacciarella. So today we're talking about planetary science, the Earth and where it fits in the solar system, how it got there, where it may be going. We're going to talk about the old ideas of how the Earth fit into not only the solar system, the galaxy, but the whole universe, and how those transformed into the new ideas. We're going to talk a little bit about the origin of the universe, how we know how that happened, or how we know what we think happened. The stars and the planets, our own solar system. We're going to talk about the Earth and the Earth-Sun system and why that creates the seasons. Then we'll get into the unique composition of the Earth, the fact that we do have this atmosphere, the fact that we have water in 3 states, the fact that we have a magnetic field around the Earth that greatly protects us from some very, very dangerous radiation. All that to be found here in Chapter 2, Earth in Space, from The Good Earth, an Introduction into Earth Science.
As you are likely aware, at one time it was believed the Earth was the center of not only, of the solar system, of the universe. The ancients really didn't perceive the solar system as a separate thing or galaxies. They just thought the Earth was in the middle of everything. And so this was the picture you see on the left, the geocentric planetary system with the Earth at the middle and all the planets revolving around the Earth. And you can see the different signs of the Capricorn as well around the Earth. The sun at the outer edge there going around the Earth, and they believed the star field was just a big sphere that essentially revolved around the Earth as well, and that was the geocentric concept of the Earth. And from the geocentric concept we went to the heliocentric, which puts the sun at the center of the solar system, and then the solar system is part of a galaxy and a universe as well. So the geocentric orbit hypothesis: ancient civilizations interpreted the rising sun in the east and the setting sun in the west to indicate that the sun and other planets all revolved around the Earth. And that really was a dominant idea for many, many, many years, more than 2,000 years. While many probably thought that this geocentric notion was not correct and something else must be going on, very few were willing to say that publicly. Of course, to say that publicly was close to heresy, was against the teachings of the Church. But the heliocentric orbit hypothesis, suggested by Copernicus in the 16th century and then confirmed by Galileo in the early 17th century through his observations. First, the phases of Venus. We saw Venus going around us, and Galileo was the first one using a telescope, which he literally invented from a French toy. It's a French toy that was used to look at pictures with 2 lenses, and he took those 2 lenses and created the telescope. He created the first telescope, and he looked at the dot that was Venus and realized that much like the moon, that Venus had different phases, and the changes in the size and the shape of Venus as observed from Earth meant that it couldn't actually be in a rotation around the Earth. And that was the first observation or data that Galileo used to begin to develop the hypothesis of a heliocentric system. Galileo used early telescopes that he again invented to look out and observe the changes in the size and shape of Venus as it revolved around the sun. Now, the 2 different illustrations represent what it would look like in the geocentric system, with the Earth being at the center of the solar system and the galaxy and the universe, and Venus actually revolving around the Earth while the sun revolved around the Earth. And if that were the case, the geocentric system, then on the top of that illustration you can see the 6 different phases of Venus. But what Galileo actually saw was this other view in which, of course, the sun is at the center of the solar system, Venus revolves around the sun inside the orbit of the Earth. And number 4 and number 3 on the right, when the Earth is on one side and then you have the sun and then the Venus is on the other side, essentially, of the solar system, you'd have almost a full Venus, as you see in 3 and 4, but much smaller because it was further away. And then as it came around the sun, we saw the half Venus and then the crescent Venus, and the crescent Venus being the largest because it was closest to Earth. And this was the new observation or the new data that allowed them to change the theory of how the solar system was set up from the geocentric to the heliocentric. Now, once it was realized and understood that the Earth was not the center of everything, and actually the Sun was the center of our solar system, it sort of redefined the paradigm of what existed, and we began to realize that we were in a solar system. That solar system was part of a galaxy, and that galaxy was part of a universe. And in fact, Earth was just simply a small rocky planet orbiting the Sun, which is a medium-sized star, and that Sun is one of billions of stars in the Milky Way galaxy, and the Milky Way galaxy is actually just one of billions of galaxies in the universe. And based on the rock record, the Earth is about 4.6 billion years old, and based on the theory, the Big Bang theory, it looks as though the universe is somewhere in the 13.5 to 14 billion year old time frame. How do we know all that? Lots and lots of different data that's come in at different times, all built together, coming in from different scientists at different times to form one unifying theory. In order for scientists to have the hypothesis or the hypotheses to come up with this unified theory, they had to have a lot of data, a lot of observations to get their ideas and their notions from. And the first bit of data that scientists using these powerful telescopes, modern day telescopes, the first observations they made was about the size and the age of the universe. Now, the size can't be measured directly, no yardstick for that, nor the age, so they use indirect measurements to estimate the size and the age of the universe. The brightness and luminosity of stars gave the first clues to just how big the universe was and how old it was as well. It also gave us an idea that the universe was expanding. Now, the brightness and the luminosity of stars, that helped us to get an idea of some of the distances between stars, but the notion that the universe was expanding was developed by looking at the Doppler effect, and Doppler with a capital D because it's named after a scientist, Doppler, who came up with this idea. He was able to look, we were able to use the Doppler effect to look at the light coming from stars and see that many of the stars, or even most of the stars, were actually moving away from us. And so the understanding of the Doppler effect and how light from distant stars changes as stars move provided more evidence to sort of show us that the universe is expanding, and more evidence and more observations in our attempt to understand the universe, and more evidence and more observations to help us come up with this unified theory of the Big Bang. So let's take a look at the Doppler effect, the apparent change in the frequency of sound waves or light waves due to the motion of a source relative to an observer. So the Doppler effect had nothing to do with stars. Doppler noticed that there was a change in frequency of sound waves or light waves, or really any radiation, due to the motion of the source of that light or sound or radiation relative to an observer. So an example, a great example, is going to be the change in frequency or the pitch of a siren from a passing police car or an ambulance. As it comes towards you, it has one frequency or pitch, and as it moves away from you, that changes. And essentially, as the source of the sound, the police car in this case, moves towards you, the sound waves are scrunched together. They have a higher frequency or a higher pitch. And as that police car moves away from you, they're pulled apart and it has a lower frequency. And that change in frequency is the Doppler effect. Now, the Doppler effect was used with light from distant stars, and that as the stars are moving away, the waves that light moved in, they were actually stretched. The radiation coming from the stars was stretched, and we can see that on the electromagnetic spectrum, that the shift in light coming from the stars, giving us our first indication that stars and most objects that we see in the heavens are moving away from not only us but each other, indicating an expanding universe. This is how you can look at light from a distant star and get the observation or the indication or the data that that star is actually moving away. Light on Earth is a form of solar radiation. So the light from the sun is actually radiation, and it's radiation that occurs at a very specific wavelength between 380 and 750 nanometers, so little itty-bitty wavelengths, and that is known as visible light. Now, all stars produce radiation and visible light at these wavelengths. So the radiation that comes from the sun is the same as the radiation that comes from other stars, and the visible light that comes from other stars also travels in this range from 380 to 750 nanometers. And you can see at the bottom of this illustration that that visible light, that radiation from 380 to 750, that is the colors of the rainbow, from our violets to our purples and blues and greens and yellows and oranges and reds, and that is the visible light. Now, when we see that white light from the sun, we are not moving away from the sun, nor are we moving closer to it. So we see that as at a fixed spectrum. Due to the Doppler effect, the color of visible light from distant stars is actually stretched. Again, it's moving away from us, so the wavelength is stretched out toward the wavelengths at the red end of the spectrum as the stars move away from Earth. So astronomers use the degree of red shift, or how far that light gets stretched toward the red, to determine the distance to faraway galaxies and faraway stars, and estimate that the most distant galaxies in our universe are at least 13 billion light years from Earth. What does that mean if the color of light from other stars is shifted toward the red end of the spectrum? Well, it tells us that other objects in the universe are moving away from Earth, and actually also moving away from each other. The further away the star, the greater the redshift, and the faster the star is actually moving away from us. So what we've also determined is not only are stars moving away very quickly, but the further the star is away from us, the faster it's moving away from us. And this has given us the data to come up with the hypothesis and ultimately the theory that the universe must be expanding. Now, light from the most distant stars has traveled more than 13 billion light years, and we know that from the amount of the redshift that's occurred. So that is 13 billion years time. Again, 1 light year is the distance that light with a speed of 186,000 miles per second can travel in 1 year. So 1 light year is about 5,940 billion miles, and that tells us that these most distant stars, 13 billion light years away, indicating to us that the age of the universe, the general age of the universe, between that 13 and 14 billion year range. Once scientists had this understanding that the universe is expanding and everything is expanding away from itself, and they got the notion of how far the most distant star is from us, that 13 billion light years, the question was then, well, what if we reversed that process? And reversing the expansion of the universe suggests that the universe began with an episode of very rapid expansion from a much more compact form. And of course, that's the notion of the Big Bang, that all space and time and energy and mass were compact into a single point, and that the Big Bang was an almost instantaneous period of rapid expansion. Prior to that expansion, there was no space and time. It was all compacted down in that one point. Now, as scientists look at some of the evidence from the Big Bang that they can find in our solar system, galaxy, and throughout the universe, they begin to understand that within hours of the Big Bang, these simple elements of hydrogen and helium formed as subatomic particles began to combine. So at the very beginning, there was no mass, just these subatomic particles, and as they began to combine, 1 proton and 1 electron making hydrogen, 2 protons, 2 neutrons, and 2 electrons making helium. And as we look at the universe now, virtually most of the universe is made up of hydrogen, and then to a lesser degree, helium. Virtually all of the mass of the universe is hydrogen, with a little bit other parts of it being helium. Then how do we get all these other elements that create everything around us? Where did that all come from? So hydrogen was what was created during the original formation of the universe after the Big Bang. Helium came from the fusing of 4 hydrogen atoms. All of the other elements and all of the other complex compounds are actually produced during the life cycle of stars. As we study stars and we see what their life cycle is, we begin to realize that stars are simply fusion engines or fusion reactors that fuse hydrogen together into helium, and then helium into more heavier and heavier elements. So all the other elements in the periodic table, all the other elements that make up everything that we see around us, are basically produced during the life cycle of stars, and some of the lighter elements just in normal stars as they burn brightly. But most of the heavy elements are actually created during supernovas, those gigantic explosions of very large stars. So just 3 elements, hydrogen, oxygen, carbon, make up about 90% of the human body, and that's by weight. 5 more elements, nitrogen, calcium, phosphorus, potassium, sulfur, make up about 9% more. So there's very small amounts of many other elements that are actually needed for life. So quite literally, even the elements that make up our entire bodies were created during the life cycle of stars. So we are essentially all simply composed of stardust. What is then the life cycle of a star? We have to again start at the beginning, and after the Big Bang there were clouds of gas and dust being spread throughout what was the growing universe, and those irregular clouds of gas and dust created from the Big Bang began to condense together to form galaxies, systems of stars. Stars and galaxies in the small section of the universe that you can see here in this picture was taken from the Hubble Space Telescope. So you're looking at both stars and both galaxies, and this is just the tiniest slice of space. Those deep space telescopes, they don't look at space in a broad range. They just take a little tiny spot, and that's what they're looking at. So everything that we see out there, whether they're stars or galaxies, was pulled together from clouds of gas and dust in the universe. And we refer to that process of creating stars as the solar nebula theory. The solar nebula theory describes an ongoing process in which gas and dust clump together to form millions of stars and to form individual stars as well. So at very high temperatures and pressures in the interior of stars, that's where hydrogen atoms are fused together to form helium. So if you look at this picture from the NASA Space Telescope, that is actually a nebula. That is a cloud of dust and gas. And as that takes on greater and greater mass, it actually begins to exert the force of gravity on objects around it. Anything that has mass exerts gravity, and the greater the mass, the greater the gravity. So as this dust cloud gets bigger, it has more gravity to pull in more dust, and eventually all that dust and gas clump together at the center. The pressure and the heat from the gathering of the gas and dust, that's what creates this heat that fuses those hydrogen atoms together to form helium. And when the hydrogen forms into helium, just a little bit of mass is lost and converted into energy, and that's the radiation we see coming from stars. So stars burn because they're fusing hydrogen into helium, and then they burn out when all the hydrogen is used up. Our sun, like all other stars, will collapse when hydrogen is completely used up. Initially, it will result in a temperature rise and an expansion. So as the sun uses up all of its hydrogen that is turning into helium, it will begin to fuse helium into heavier elements. Well, that will result in more heat. More heat means expansion, and our sun in the next 4 to 4.5 billion years is expected to get hotter and hotter and literally expand out to the size of about the Earth orbit. Higher temperatures would fuel more of that fusion, which converts helium into carbon, and that conversion of helium into carbon just releases more energy and more heat. The fusion would end when all the helium is used up. Carbon is too heavy of an atom to be forced back together in a sun, and so the loss of heat of fusion would then allow that star that's expanded out to Earth's orbit to collapse in on itself. So that would be a white dwarf. It'd still be hot, and eventually that white dwarf would cool into what's called a black dwarf. So the life cycle of our sun started out as a clump of gas and dust that through gravity got denser and denser and denser until the heat of the pressure and the friction from the mass rubbing together was able to fuse the first bit of hydrogen into helium. And in the life cycle of a star the size of our sun, about 8 billion years, throughout that life cycle converting hydrogen into helium, and then when all the hydrogen's used up, beginning to convert helium into carbon, that being a hotter process causing the sun to expand and expand and expand. Then when all the helium is used up and no more fusion can occur because again carbon too heavy to be fused together, then it collapses on itself, still hot, so it's a white dwarf, and then as it cools, transitioning into a black dwarf. When I mention the size of our sun, that sort of infers that stars have different sizes, and in fact they have much variation in size. We have giant stars, we have medium-sized stars, we have smaller stars. Giant stars burn very brightly and burn out much more quickly. Medium-sized stars may burn longer. For instance, giant stars are about 100 to 1,000 times brighter than our sun, so they burn out in about 10 to 20 million years, where intermediate-sized stars, such as the sun, they typically last somewhere between 8 and 10 billion years. So this diagram we're looking at basically shows different types of stars. It also gives a luminosity of those stars. So how luminous is it relative to our sun, with some of those gigantic delta and Rigel being as much as 10,000 times brighter than our sun. Then it also gives the temperature in Kelvin of the surface of the stars. And again, those bigger stars are much, much hotter. But it also gives us an idea of how long those stars will last. Now, our sun is on what's called the main sequence, right there in the middle, and it's a medium-sized, intermediate-sized star, which again should last about 8 to 10 billion years, and we're about 4.5 billion years into that life cycle. Intermediate-sized stars like our sun do not have the mass, the pressure, or the heat to fuse elements together any heavier than when the helium is fused into carbon. But larger giant stars, they do have the heat and the pressure and the intensity to fuse heavier elements. And so giant stars collapse over multiple stages. Hydrogen turns to helium. The helium forms carbon, and it gets much, much bigger. And then when they finally begin to collapse, the collapse of those stars is enough pressure to form increasingly complex elements. So the carbon then forms oxygen, and so on and so on. So in the ultimate collapse of a giant star, that is what is known as the supernova, which is the massive explosion. And the supernova is the one moment in time when there's enough heat and enough energy to actually fuse all the heavier elements that exist on the periodic table, all the heavier elements, the silver, the gold, the aluminum, the silica, magnesium, manganese, whatever it is, all of those heavier elements are fused from those elements of carbon and oxygen and helium and hydrogen during the supernova. And not only are they fused together to create those elements, but they're also scattered into space by that explosion. So those clouds of gas and dust that I was talking about, that were the beginning of the solar nebula theory, well, those clouds of gas and dust come from these supernovas. Now, the first clouds of gas and dust came from the Big Bang, but once the first stars were formed, specifically the first giant stars, the ongoing process was stars formed, hydrogen turns to helium, the star turns itself on, radiation moves away from the star in the form of light and heat, it burns, it burns, it burns. When it finally collapses and explodes, the giant star, it throws out all those heavier elements into the atmosphere. And here's a great Kepler's supernova, and that was taken, the supernova is expected to have occurred in 1604, but we're still getting pictures of it at this time. Back to the solar nebula theory, when our cloud of dust and gas finally begins to fuse the first hydrogen into helium and the sun is born, those early suns, those early stars are surrounded by the cosmic debris that was that cloud of dust and gas. And as gravity pulls it into the center or toward the center of the star, they begin to rotate. And so new stars are surrounded by these rotating disks of cosmic debris. As that debris rotates around the new star, gravity in those larger clumps again pulls debris in that sticks to the clump, and the clump gets bigger. The bigger clump has more gravity that pulls more stuff in. And literally through the process of accretion, planets form. So gravity pulls debris together to form planets that then revolve in a consistent direction around the star. So all of the planets not only revolve in a consistent direction. If you look down on the sun from the top, they all go around counterclockwise. They're all essentially on the same plane. Now, they're not exactly on the same plane, and some get knocked off that plane by interactions from gravity or maybe even collisions with other objects. But essentially, they're all on a plane called the plane of the ecliptic. Now, because gravity works as it does, the heavier stuff is pulled to the center, so the heavier, rockier planets are closer to the star, and the lighter gases typically are further away from the star. And as we look at the formation within the solar nebula theory of our solar system, we realize that many, potentially thousands or millions of other solar systems exist that very likely have planets that revolve around those stars as well. So our solar system is made up of our sun and the surrounding planets. And the sun makes up about 99.8% of the total mass of the solar system. Sun happens to be about 150 million kilometers, or about 93 million miles, 93 to 95 million miles from Earth. That is one astronomical unit. That when we talk about distances, we use the distance between the Earth and the Sun as one unit because the distances are so large. But that's the distance from the Sun to the Earth, about 93 million miles. And what's interesting about the Sun is it undergoes differential rotation. The Earth all rotates at the same speed because it's solid, but the Sun is not. So the Sun's equatorial region rotates in about 25 days, and the polar regions take about 36 days to rotate. So this results in some major disruptions of the Sun's magnetic field, and that's where we get the sunspots and the solar flares that we see on the Sun. Like just about everything else in nature, things run in cycles, and there's actually a cycle to the frequency of sunspots. At the solar maximum, we may see as many as 100 sunspots at a time, and then at the solar minimum we may see very few sunspots, and that difference between the minimum and the maximum typically runs about 11 years. And sunspots and solar flares can have an impact on the Earth as they throw energy in the form of a solar wind toward the Earth. Typically our magnetic field deflects that energy, that solar wind, but on these times of very high activity during the solar maximum, it can disrupt some communications and satellite communications on Earth. Space weather, and yes, there is such a thing as space weather, is dominated by this solar wind, a constant stream of charged particles emitted from the outer layers of the Sun's magnetic field. The solar wind affects a volume of space known as the heliosphere. So the heliosphere is this massive basically globe around the Sun that encompasses all the solar system and well out beyond the solar system, where the solar wind actually affects space. And the heliosphere is that region of space in which our Sun is a dominant influence. The heliosphere again extends far beyond the solar system. Now Earth's own magnetic field, as you can see in this particular illustration, deflects the solar wind around our planet, helping to protect our atmosphere. Without that magnetic field, our atmosphere would be stripped away, and that's what's happened on other planets in the solar system that do not have atmospheres. It was stripped away by the solar wind. In our solar system, the solar wind emanates out from the Sun, creating what's called the heliosphere, this massive globe around the Sun which goes out way out past the outer reaches of our solar system. And the interactions of the solar wind with the Earth's magnetic field can also generate beautiful visual effect, the aurora borealis, the northern lights. That all happens in the upper atmosphere of the polar regions as the solar wind excites some of the molecules in the upper layers of the atmosphere. But occasional solar eruptions can also disrupt the Earth's magnetic field to produce electrical blackouts. Satellites are in greater danger from solar flares than features on the surface, but it can disrupt communications on Earth because of solar flares. So the solar wind is a dangerous thing, and our magnetic field definitely protects us from it. Here's your standard illustration of the solar system with our Sun, and of course Mercury, Venus, Earth, Mars, those the terrestrial planets, Jupiter, Saturn, Uranus, Neptune, the Jovian planets, and Pluto as the dwarf planet, no longer part of the 9. Now we just have the 8. And one of the reasons why Pluto, you can see not quite on the plane of the ecliptic, it's a little bit well, it's quite a bit skewed from the plane that the other planets are rotating in. You can also see between Mars and Jupiter, we got a bunch of asteroids there. That's the asteroid belt. And then well out beyond is the Kuiper belt, where that comet is coming from. Pretty standard stuff. You can see the composition of Mercury, Venus, and Earth and Mars, very, very similar with the cores and the mantles and the crusts, and the composition of the Jovian planets, the gas giants, Jupiter, Saturn, and Uranus and Neptune, with a little itty bitty bit of rock in the middle, mostly a lot of water and ammonia and hydrogen, liquid hydrogen, and different types of gases. Here is more information on our 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, the size, the orbital period, the distance from the Sun, and again, we can see the different atmospheric gases. And if I point out distance from the Sun in millions of kilometers, or in AU, astronomical units, where the Earth is 1 astronomical unit from the Sun, and then Jupiter is 5, Uranus is 19, and Neptune is literally 30 times the distance from the Sun as the Earth is. And you can see almost to scale here the difference between the terrestrial planets and the gas giants, and with Jupiter, of course, being the largest gas giant. But we always think of Saturn as having rings, but all of the gas giants actually have rings around them. Again, the planets in our solar system divided into 2 types, classified into 2 types. I'll tell you many times during this course that scientists, their whole job is to classify things. Well, if we're going to classify our planets, there's 2 classifications. Terrestrial planets, which are rocky, and the Jovian planets, which are mostly gas. So Mercury, Venus, Earth, and Mars, those rocky terrestrial planets close in, the heavier elements being pulled close to the Sun, and the lighter elements of the gases making up the Jovian planets of Jupiter, Saturn, Uranus, and Neptune. So what about Pluto? Well, as we said already about the scientific method, when more data, new observations come in, we have to be able to change our original theories. So the theories as to the structure of the solar system, having the 9 planets, including Pluto, it had to change when we began to realize that Pluto wasn't really like a lot of the other planets, well, like all the other planets. Improved technology resulted in recent discoveries that there were several distant objects that were basically similar in size or even larger than Pluto that were orbiting the Sun at that distance. So the International Astronomical Union, group of scientists, got together and they decided that they needed to do something. They either needed to consider the new objects as new planets, because again, similar or even larger than Pluto, or they needed to classify the new objects, including Pluto, as a new group, and they decided to go with option 2. So the IAU adopted a new definition for the term planet. A planet is an object that orbits a star, that's 1, orbits a star, and is massive enough, 400 kilometers in radius or larger, for gravity to pull its material into an approximately spherical shape. So gravity has to be strong enough to overcome rigid bodily forces and bring the material into a spherical shape. And then the last of the 3 criteria to be a planet is a planet has to have swept its entire neighborhood of any other debris in its orbit. So Earth has swept up all the debris in its orbit. Jupiter has, Saturn has, Mercury has, but Pluto hasn't. There's other debris about the size of Pluto or even bigger in its orbit. Pluto does not meet the last part of the definition and was considered a founding member of a new class of objects. Those would be dwarf planets. Pluto is a dwarf planet. Terrestrial planets then are composed of rock, and terrestrial planets are divided into compositional layers. As these planets were forming, the early planets, sometimes known as protoplanets, just imagine a big rock moving around the Sun, and as it moves through its orbit, it bangs into other smaller rocks, and rocks stick together, and the rock gets bigger and bigger. And as it gets bigger and bigger, its gravity gets larger, begins to pull more and more other bits of space debris and rock and gas in. And as it gets bigger and bigger and bigger, the gravity gets stronger. That gravity creates pressure, and then everything kind of banging into it, and the friction of the gravity moving things around creates heat, and the friction and heat begins to melt the interior of that protoplanet as it's getting bigger and bigger and bigger. And we expect that those early planets were largely the same throughout. homogeneous. They just had the same material molten throughout. But as it got bigger and bigger and gravity became stronger, the heavier elements, like iron and nickel, got pulled to the cores of these planets, these terrestrial planets, and the lighter elements migrated out to the mantle and to the crust, like the elements of silicon and oxygen. So terrestrial planets are divided into compositional layers based on the how heavy the elements are, with the heaviest elements at the center. Now, if we take a little cutaway of the top of the mantle and we see the crust, both the oceanic crust and the continental crust, we see the crust lies on top of the mantle, but the mantle actually has two separate parts. Most of the mantle just below the continental crust is this lower part called, and the oceanic crust, the asthenosphere. And the asthenosphere is a plastic layer in the upper mantle, meaning it's not quite moving, it's not quite solid. Imagine candle wax that's not cold, but just slightly warm enough that maybe you can mush it just a little bit. That's the plastic layer of the asthenosphere. And on top of that is that rigid upper mantle, the lithosphere, with the continental crust on top of it. And that difference between that slightly plastic material and that rigid material above it, that is the natural process that allows for seafloor spreading and continental drift. And this is going to explain the theory of plate tectonics. And we're going to talk more about that later on in the chapter, or in the class, that is. The Jovian planets are the large gas giants, the last four planets in the solar system. Much of the volume of these planets is made up in a thick atmosphere that's on top of these oceans of liquid gases that cover up the much smaller rocky cores of the planets. The Jovian planets all have moons, lots of moons, and they all also have ring systems. Now, we really only see the rings of Saturn, but all the Jovian planets have rings, and again, they all have these moons. Now, when we look at the four largest moons of Jupiter, they play a very important role in the transition from the geocentric to the heliocentric model of the solar system. As Galileo was looking out and seeing the different phases of Venus, giving him the idea that, well, maybe stuff isn't rotating, maybe it's not revolving around the Earth. He also saw every night, he could see Jupiter as a bright spot, but he could also see much smaller little dots of light around Jupiter, which were in fact these Jovian moons, these four of Jupiter's largest moons. And he realized that they were there every night, the same place, at the same time, that they were not revolving around the Earth. Those moons were not moving around the Earth. And if they weren't moving around the Earth, maybe nothing else was. And that was a big part of the transition from the geocentric to the heliocentric model of the solar system. So let's talk about the Earth and why the Earth is so special. The Earth is so special because it has water in three different forms: solid, liquid, and gas. And why is that? Because it's just the perfect distance from the sun, that it's warm enough to sustain life, but not so cold that you can't have liquid water. So what makes this planet so great? And there's some unique things happening with the planet. And specifically, the sun, the Earth, the interaction between the two, helping to create the seasons. So why is it hotter at the equator than at the North Pole? Well, the North Pole is further north. It's colder up north. Well, why is that? The absolute answer is because the equatorial regions receive more solar radiation than the polar regions. And if we just first look at this illustration, at the equator, where the noonday sun is directly overhead, straight overhead, the sun comes in and the same amount of sunlight warms a much, much smaller section of the Earth, as does what's happening in the polar regions, meaning at the same time, the same day, the same little ray of sunlight has to come in and warm a much, much larger section of the northern latitude. So the further north you are, the less amount of sunlight each little spot on the Earth receives, because at the equatorial region they receive more of that solar radiation, known as insolation, incoming solar radiation, then the equator is going to be warmer. The amount of solar radiation reaching the Earth's surface depends on the angle the sun's rays strike the Earth. At a much greater angle, up around 90 degrees, more heat is delivered by insolation where the sun is directly overhead. as sunlight is distributed over a smaller area. The total annual insolation is the smallest at the poles and the greatest at the equator. So you can see by the illustration, solar energy is diluted over a larger area when the sunlight strikes at a low angle, such as at high latitudes. It's not diluted, it's over a much smaller area when it strikes at a high angle over the southern latitudes. Seasonal temperature contrasts are due to the amount of insolation, incoming solar radiation, reaching the Earth. Seasonal differences in insolation are due to the tilt of the Earth's axis and the angle of the sun rays. So the tilt of the Earth is 23.5 degrees. The Earth is tilted on an imaginary axis oriented 23.5 degrees to vertical. So the Tropic of Cancer, which is that line there to the north, and the Tropic of Capricorn to the south, those are lines that are 23.5 degrees north and south of the equator. And as the sun moves, when the Earth moves around the sun, the tilt of the axis always points in the same direction. So at one point in the Earth's journey around the sun, the Earth is tilted toward the sun. The northern hemisphere is tilted toward the sun. At the same time, the southern hemisphere is tilted away. When the northern hemisphere is tilted toward the sun, that's the northern hemisphere summer. When the southern hemisphere at the same time is tilted away, it's the southern hemisphere winter. You can see from the illustration that no matter where the Earth is in its trip around the sun, the axis is always pointed to the same spot in space. So upper right hand corner, wintertime, December 21st, the winter solstice, the northern hemisphere is pointed away from the sun, so the northern hemisphere is going into winter. Opposite side of the illustration, summer solstice around June 21st, the northern hemisphere is pointed toward the sun. Because the northern hemisphere is pointed toward the sun, the rays of the sun are more direct and provide more heat to the northern hemisphere, and therefore you're in summertime. At the equinoxes, both September and March, that axis is still pointed at the same spot, but you're basically on the side of the sun, so the entire hemisphere is getting equal parts of day and night, and those are the beginning of spring and beginning of fall. Equal parts of day and night, why they call them equinox. The sun is directly overhead at different places during different times of the year, during the different seasons. During summer in the northern hemisphere, the sun is directly overhead the Tropic of Cancer, that northern line. During the winter in the northern hemisphere, the sun is directly overhead of the Tropic of Capricorn in the southern hemisphere. During spring and fall, the equinox is now in the northern hemisphere. The sun is directly overhead the equator. So the Earth's axis is always tilted in the same direction. That causes the distribution of solar radiation to change with the season. That's ultimately the reason why we have the seasons, the change in the amount or the distribution of solar radiation due to the Earth's tilted axis. So it is the tilt of the axis that causes the different seasons. Because of the tilt of the axis, in our wintertime, the northern hemisphere is pointed away from the sun. In our summertime, the northern hemisphere is pointed toward the sun. It is not the distance from the sun that causes the seasons. This is a common misconception. It's not the distance from the sun. As a matter of fact, when we look at the slightly elliptical orbit around the sun, it's almost a circle, but just slightly elliptical. We're about 152 million kilometers in the summertime and about 147 million kilometers in the winter. So we're actually closer to the sun during what's known as our perihelion. A perihelion is when a celestial object is closest to the object it's orbiting. The aphelion in July is when we're furthest from the sun, and that's actually our warm season where we're farther away. So it is not the distance from the sun that creates the seasons. The tilt of the axis also causes us to have longer days in the summertime, and the amount of sunlight during any given day is known as the photoperiod. So a longer photoperiod in the summertime than in the wintertime. And the best way to see that is, let's look at the top illustration and look at the northern hemisphere. And we can see the Tropic of Cancer. That is the black line going through North Africa there. That center black line is the equator. To the south is the Tropic of Capricorn. But the Tropic of Cancer, the black line moving through the northern Africa, you can see that it has a much longer distance to travel if you take it from that point all the way to the edge of the globe than the Tropic of Capricorn that moves from the east side of South Africa. It is a much shorter distance. So that northern latitude has a longer day than that southern latitude. And that is because, again, the tilt of the Earth. So with latitude, higher latitudes have more daylight than low latitudes in summer, and then it's the opposite in winter. So it's always the case that you have longer days in the summertime than you do in the wintertime, and that also helps to make it warmer in the summer. Again, as a terrestrial and rocky planet, the Earth has a fairly unique composition as well. The interior can be divided into three major compositional layers: the crust, the lighter elements of silicon and oxygen, the mantle, composed of rocks made up of three key elements: oxygen, silicon, and magnesium, and the core, mainly iron and nickel. But what's most important about the core is the inner core is solid, and the partially melted outer core kind of moves around that solid, and it's that difference between the solid inner core and the partially melted outer core that creates the Earth's magnetic field. And it's very important. That magnetic field is what protects our atmosphere from the solar wind. Also, as we've already discussed, in addition to the three major compositional layers of the Earth, the core, the mantle, and the crust, scientists recognize two layers with different properties near the surface: the lithosphere, the rigid outer layer composed of the crust and upper mantle, and the asthenosphere, the plastic, slowly flowing layer in the uppermost part of the mantle. The lithosphere is literally divided into large slabs known as tectonic plates. Again, this is the theory of plate tectonics. Plates move over the Earth's surface to produce earthquakes and volcanoes, mountain belts, and various features on the seafloor. And this illustration shows us the many, many different interactions of the oceanic crust and the continental crust, and what's happening in the asthenosphere and the lithosphere. And we're going to talk in great detail about this when we talk about plate tectonics and that theory of continental drift. Another unique property of the Earth is the geothermal gradient. Earth's temperature increases with depth. The average temperature rises about 25 degrees Celsius for every kilometer that you go down into the ground. Now, heat is generated by, the formation of the planets. All the terrestrial planets cooled following formation. Only large planets like the Earth actually still retain that heat. Plus, there's radioactive decay of elements occurring in the Earth's interior that also releases heat. And so the Earth has this geothermal gradient where it gets hotter as you get deeper. So what makes Earth, that actually shares many, many features with other planets, so special? We have liquid water. Many of the other planets have frozen water or some level of liquid gases, but we have liquid water. We have gravity and a protective atmosphere. We have life-sustaining gases and a strong magnetic field because we have a solid core with a liquid outer core around it. So there's a lot of great unique properties of Earth that allow it to sustain life. Liquid water, of course, essential for life on Earth and is maintained by that appropriate temperature range between 0 and 100 degrees Celsius. Venus is too close to the sun. Originally, all the water evaporated in the atmosphere, and those water vapor molecules split by ultraviolet radiation and hydrogen are essentially lost into space. Mars, too cold today to have liquid water. There's some frozen water there, but that liquid water is one of the things that makes Earth so unique. Earth's size is sufficient to produce enough gravity, so we're big enough to create enough gravity to hold a nice thick atmosphere of gas in place over the Earth. And that atmosphere is so important because it protects us from incoming asteroids and comets. And that doesn't happen every day, well, not big ones anyway, but it also protects us from the harmful solar radiation, X-rays, and ultraviolet light. So that atmosphere is very, very important to us. We know that Earth is unique in that its biosphere has actually altered the composition of the atmosphere. How is that? Well, in the beginning, Earth was, the atmosphere is mainly a lot of nitrous, a lot of methane, a lot of CO2. It wasn't until there was the first blue-green algae plants that took carbon dioxide in and released oxygen. So there's a very long period in the Earth's history known as the rise of oxygen, where carbon dioxide was taken in by plants and oxygen was released by plants. Now, very important because carbon dioxide is a potent greenhouse gas. For instance, on Venus, where higher carbon dioxide content exists, temperatures are about 464 degrees Celsius. So the lack of carbon dioxide and the oxygen has been a big benefit to the Earth, all created by the biosphere. The composition of the Earth's atmosphere is just right to absorb enough heat to keep average temperatures at about 59 degrees Fahrenheit. So when you take the globe, the entire globe, all times, all places, the average temperature is about 59 degrees Fahrenheit. Without greenhouse gases, so part of the Earth's atmosphere, not only oxygen, but are these other greenhouse gases like water vapor and carbon dioxide and methane. Without those greenhouse gases, the average temperature would actually be 0 degrees Fahrenheit, well below freezing. So if you look at the left and the right illustrations, this gives you an idea why. The incoming solar radiation from the sun is in a very short wave, and that incoming short wave radiation passes through the atmosphere. It's absorbed by the Earth, and the Earth heats up, and then the Earth emits long wave radiation in the form of infrared or heat. If there was no atmosphere, like you see on the left side, the short wave incoming solar radiation would come through, strike the Earth, warm the Earth, and then all that heat from the Earth would just escape into space. With a protective atmosphere, the incoming shortwave radiation passes through the atmosphere. The atmosphere does not absorb the shortwave radiation. The shortwave radiation heats up the Earth. The Earth re-radiates. It radiates away its infrared energy. Some of it does go out to space, but much of it is absorbed by the atmosphere, warming the atmosphere and keeping that constant temperature at about 59 degrees Fahrenheit. So that thick atmosphere is just perfect to keep the Earth at just that perfect temperature of 59 degrees Fahrenheit. Insolation, or the incoming solar radiation, which is a shorter wavelength, largely passes through the atmosphere to be absorbed by the Earth's surface. The infrared IR radiation, the heat that we feel that is a longer wavelength, is emitted by the Earth. It tries to escape to space, but part of it is absorbed by the greenhouse gases due to it being a longer wavelength, and that's what keeps the Earth warmer. So the greenhouse effect is very important. It's just the runaway greenhouse effect that could cause global warming. All right, lastly, the Earth's magnetic field protects Earth from harmful solar winds that would strip away the atmosphere. Because of that magnetic field, due to the molten rocks in the outer core and the relatively rapid planetary motion, we get this magnetic field. Smaller planets or slowly rotating planets have lost heat, and therefore they have a very weak magnetic field. Because we have this very rapid rotation and this molten rock in the outer core, we have a strong magnetic field. And that magnetic field literally protects the Earth from the solar wind that would typically strip away our atmosphere. So again, the Earth is very unique. It's life-sustaining, liquid water, and just the perfect temperature. We're going to talk about some other parts of the solar system that actually create a threat for the Earth, asteroids and comets and near-Earth objects, coming up in Chapter 3